Hello, so now welcome back to our study session. Today's subject will be hydraulic, which is the fluid mechanics, or yeah, we only have two words for this subject. So today our topic will be pumps, P-U-M-P, pumps. Why am I not writing this? Pumps will be our topic today. So before we get started to the exercise or problems, I would like to show you some words or like we call it technical terms that we use in our exercise or yeah, basically in this chapter. So we have we can call it the terminology, and we have many words that we haven't like encountered before. So now we have the study cat. Steady cat is like like the elevation in free water that is compared to the reference datum. So this is like the datum here, right? The reference line, or we can say that the reference datum, and like if there's like the water here, so here's the surface, right? Surface. So that is compared to the datum here is called the steady cat. I will give you another specific, like the specific diagram for this terminology. So steady cat, we have the abbreviation of H, capital H, stat. So here's the capital H. Don't because we have a lot of H here in pumps like head, headless, and but basically steady cat must be the capital H because like it's the biggest thing here, and we have the static suction head. So static suction head. It's like the difference between the suction liquid level. So like the suction liquid level compared to the center line of the pump. So here we have, you see, it's like the smaller s, not the capital S anymore. So don't forget, like, don't get it mixed in between. So for example, we have, this is the pump, right? The pump and the symbol will be something like this. So the flow rate is going this way, right? So this is the center line, and so suction head is like the suction liquid level, and compared to this pump line here. So now we have suction head, this like suction liquid level, suction liquid level. And for the another terminology that we have here is the static discharge head. So now we have the same here, but it is called a discharge head. Its abbreviation is HD, and this is like mainly focuses on discharge liquid level. So now we have this one here as well. Okay, so now we move on to how do we find this one, the static head here. So the static head here is equals to HD minus HS. So as a diagram, like I will attach a diagram for you to like actually see clear. Okay, so how do I draw this one? For example, we have I need to draw it like nice and neatly, right? So we have water here, and there's like the pipe, yeah, the pipe that is going that way. We have another water tank here. So in this subject, we're only studying about water. Okay, so now we have here and here. So there's like the pump. How do I draw the, yeah, I can just draw the symbol of pump, right? So now we have the pump here, and the pump here is also connected to the upper part, so I will draw it something like this. Okay, So now we have two surface, the surface of the water. Should I use it in another like color? So like, yeah. So this is the water, and this is the water. So here is the what do we call it? Like the static suction head. So the static suction head is HS, and this everything here is HD, and this tiny little thing here is the total static head. So this is the reason that like we have HD minus HS that is equal to the star, that is equal to that one. So we have in another case that the pipe is not like this. So here we have same, we have two tanks. So there are times that like we compare it to the center line, the center line of the pump. Okay, so but this time this cute tiny little thing is going downwards here, and it's going this way. So we don't have this one anymore. We have as this one. So now we have this one is the what do we call this one? The surface of the water. So we compare it to the center line of the pump here. We can see that this is shorter, and this is the HS, and this, okay, so wait, we don't have this line, and this is the HD. So now we have this one, the total static head. So as you can see that sometimes the total static head can be shorter than the HD, but there are also sometimes that total static head is like combined between the two. It's like HD minus HS. So we have HD plus HS equals to the head stat. So for if you wanna be like in the simple terms, if you put it in simple terms, it's like from surface to surface. So this is a surface, right? This is a surface. So from surface to surface, and this is a surface. This is a surface from surface to surface, and that's it. That's the simple thing, the simple ideal concept that we're going to use in this one. So that's not all for our terminology. We have another one which is three other ones. So now we have friction head loss, which abbreviated to HF, and we have the minor head loss, which is abbreviated to HM. So this is everything that we have here, and the final grand total one, which is the TDH. So H stands for head, D stands for dynamic, and T stands for the total. And all of these we can just write it into HT. So this is like the grand total of all heads required to deliver. Like we have this one is the liquid A, tank A, and this is tank B. So in order to flow here, how many head do you need to require to deliver from this to this? Oh, this diagram is not good actually. There's no pipe that is like this. Up. Okay. So this is like the pipe here. From point A to point B, how many, like the grand total heads that required. I'm gonna delete this because it's not looking good enough. Okay, so now we have all the terminology. We have let's go through again. We have H stat, HS, HD, HF, HM, and HT. Everything is all in H. And don't forget that we have different capital letter and big, small letter and capital letter. So now we have this problem. Yeah, problem, not exercise, because this is actually like painful. So we can say that it's a problem, because exercise will like make you fitter when you see another exercise, right? But it's like a problem, like it's the start of it. Okay, so now I made a mistake, so I'm sorry. We're not going to calculate the pressure, but we're calculating the power, because like it's P, so I confused between pressure and power. So in this case, it is power. Okay. So now we calculate the TDH as we have learned earlier. The total dynamic head is the TDH. Actually, I wanted to give you like all the formulas before we are doing the exercise, but I'm afraid that if we're doing the exercise and like looking at the formulas simultaneously, we will learn better. So, okay, let's get started. So now read the problem carefully. We want to find the TDH and the power here. Given that Q equals to 0 and we neglect the central line of the pump. So now there's no pump. Like imagine that this is put into white. There's no pump here. Just imagine there's no pump here. Does this make sense? There's no pump here. Okay, so come back to this one. Did I use this? Okay. How do we imagine this? So this is all here, and this is, oh no, I mean this one here, because this is the water level, the surface water level here. So it's gonna be something like this. This is 1.5. This is 37 meter. Am I right? 3 minus this one. Okay, so now we have the total static head. And then we are, so I'm gonna give you the formula now. TDH equals to static head plus friction loss, or friction head loss, and then we plus the minor loss. So basically we have another term that we need to consider, which is like it is related to Q, but we don't have the Q here. So yeah, just ignore the Q here, because they say that the Q equals to 0 here, given that Q equals to 0. So now we have the static head here, which is H, capital H stat, and we have the friction loss, which is the H, the small hf, and the hm plus. Okay, so now we have this one. So 30% of the equivalent head is like 0.3 of this one. So 10 here equals to 3m. Now we have everything that we need. So the static head that we have here is 35 plus 2. So H stat equals to 35 plus 2. So this is like the bigger part here, and this is the HF. Okay, so I'll say this one is H D H. Actually, the D is supposed to be smaller, okay? And we minus HS. So here is it's going downwards, right? This is the ground level, so it's going downward here. It's supposed to be minus 1.5, and this is the HS. But I'm going to write it as, clearly it's minus 3.5 plus 2 here. Yeah, so we get minus 1.5. So the total value is 38.5. Am I right? Yeah, 38.5 meters. Now we have the HF, which is equals to 10, and HM equals to 0.3 minus multiplied by 10 equals to 3 meters. Or we can write it this way, this one here equals to 130%, which is 10 multiplied by 1.3, which is 13. So it's the same way around. So we have everything that we need. We can find a TDH. So don't forget TDH can stands for like HT, the capital HT. So TDH equals to 38.5 plus 10 plus 3 equals to 51.5 meters for the TDH. So now we have come to the end of the first question. Now we're finding the power. So how can we find the power? What formula are we going to use for the power? So now we have another new, is a brand new formula that we have here. It's called the efficiency. So this efficiency, it's E equals to, I forgot this one, gamma QHT over P, power. I repeat, power, not pressure, because like there are a lot of like, sometimes you use pressure, sometimes you use like, you know, in the water, but this time it's power because we're talking about the pump, right? So how much, not how much, how much power should we use to generate this, kind of pump? So now we can see that P equals to, okay, so now we have P here. You just rearrange the equation. So now we have E here. We get so of course it is water. I forgot to tell you in the beginning of it, it's water. And or M2 S square. Actually this comes from, like, G, this one, right? 9.81. Yeah, and then we get this one. Should I write it neatly? Neater than this one. 9810 kilograms M square S square. So now we have this one. Then we go to the Q, which is 100 liter. Liter is actually decimeter cube over minute. Yeah, where is this from? It's from this one here. And then we multiply by, we have to convert this one to M. Yeah, because you can see that this one is M and this one is second. So how do we convert this one? It's just, chaotic. 10 per decimeter square, like this. Does this make any sense? So this is like one in 1 meter cube we have 1,000 decimeter cube here. Oh yeah, I'm right. So then this is not enough. Yep. And then we have the convert from M here, convert the S here and the minute here. So now we multiply by like this. Oh, okay. You might confuse like meter per second, so it's like mean per sec. I hate converting this. So in 1 minute, we have 60 seconds. And then we multiply by the last one, which is 51.5 M. And where is this from? It's HT. And the overall thing is the efficiency. Oh, I forgot to tell you. The efficiency is actually why did I forget so many things? Efficiency is like from this one. Like there will be some variable in here. Efficiency is equals to 75%. So yeah, this is the overall thing here is 0.75. So the total number here is 227 watts. This is the end of this exercise. So now we have this one as the second answer, and this is the first answer. So this is 51.5 M, and this one is 1122.7. It's pretty simple, isn't it? So now let's move on to another interesting exercise that involves in some part of fun thing. Dun dun. Okay, so what diagram is this? Why is it so it is not that complicated diagram yet. So now let's read the questions one by one, thoroughly. Do we use this word? No, I mean like clearly. So now we can see that this centrifugal pump is what we're studying. It's the pump that we're studying. Has the characteristics shown in the figure. It is used to pump water between two large open tanks through, why is it in feet again? 100 feet of 8 inches diameter pipe. So the pipe here is, the diameter is 8 inch. So it's like getting the flashbacks of Hazen and Darcy. That is like, such a hassle. Is it Hazel or Hazel? Yeah, just move on to this one. So this pipe contains 4 regular flank 90 elbows. So elbows is like this. Sorry for my awful drawing. So it's like this 90 thing here, and we have a check valve. So we have elbow, check valve. We have a fully open globe valve, and other minor losses are negligible. So assume the friction factor as this point and the 100 feet section of pipe. If a static head, so this is like they're telling the static head is the difference between fluid surface of 2 tanks, which is like this one. This is the surface here, so it's like, why am I doing this? Yeah, from this to this. So for example, if we don't have this one, so we can say this is the HD here, and this is the HS. So it's like this won't be just 1.5. It must be something else here. Yeah. So there might be some differences. So in this case, thanks to the neglect of the center line of pump. Okay, so now let's continue with another problem. It is called it is related to the centrifugal pump that is like having the impeller diameter of 1. So I'm gonna highlight everything that is important. I'll use another color. So it is constructed so that it will supply a head rise of 200 meters, a flow rate at 4.1 cubic meter per second of water when operating at a speed of 120 rpm rounds per minute. So now we have to study the characteristic of this pump, and it is called the 1/5 scale, geometrically similar to the motor operated at the same speed. So it says same speed. This is the speed, and this is the speed. So to be tested in the laboratory. So now we have 1A, determine the required motor discharge. So we have the motor pump that must operate at the same flow coefficient, so that we have a new formula that we're going to study today, that we're going to face today, not to study. So now we find the required motor discharge. We have this equation Q, which is the flow rate, over this one is the angular speed, or we can just say speed, yeah, over d to the, what is this, d to the cube to the power of 3. So this is the m equals to the q d. So this is the same here, but now we can find the qm. P. Okay, so we have the qm here, q model, pump, model and pump. So qp here, how do we do this? We only want this part, so everything here must move to this. So now we have there's a okay, stays the same here, and P M D M cube. Okay, so now we can write as Wm over Wp multiplied by dm cube over dp cube multiplied by qp. Okay, so now we have everything here that we find the flow rate of the model pump here that we have. So now we can see that this is the speed. So it says it mentions earlier that the same speed. So we have 1/1, and this it is mentioned here that the scale here is 1.5 scale. So it's supposed to be 1/5 cube here multiplied by qp, which is 4.1 here. So q is the only thing with the unit, because everything else is already cancelled out with because this is the same unit, so things are cancelled out, and the final answer we have 0.0328 meter cube. So this is the answer for the flow rate, that the same. So to make it similar, we have to have these equations, the two equations equal, so that we can see that it has the same flow coefficient, and then we can find the required motor discharge. So now we move on to question B. Determine the head rise. So head rise refers to h. So now we can see that both model and prototype operate with the same efficiency, so therefore the flow rate is the same. So if the efficiency is the same, so therefore the flow rate coefficient is also the same. Okay, so now yeah, so this is what we have here. So then we can use another formula that we have never encountered before as well. So now we can write as B, find the head rise. So in this thing we keep comparing things together. Like, you know, there's two equations, and for two equations that have the same coefficient or same something that it mentioned in the problem. So we have model and GHA W. So H is like the head rise. Oh, not W, it's like omega, I guess, if I'm not wrong. From here. So now we're finding H. So HA is actually similar to the first one. So we want to find this one. So HA equals to GHA here. Okay, and then over omega square, the angular speed, model square dm square, and this is p, but this one is it's going down because it's on the upper part, it has to go down, and the lower part has to go up here. So now we have 1 over G M P. Okay, so now we have everything that we want. We can find the HM is equals to 1 and multiple by 1 square, multiple by 1 over 5 square, multiple by 200. 200 is from this one. I lost it again. But it's 200. Here. The head rise. It will supply the head rise. So now we can find the H A of M model equals to 8.0 meters. So this is the answer of this problem. Okay, so now we have another problem. It is related to the horsepower, and again it is related to, you know, the CFS cubic meters per hour. Oh, cubic meter per second. Cubic feet per second. Okay. This F here is supposed to be the Fahrenheit. And so now we can see that what horsepower must be supplied to the water to pump 2.5 cubic feet per second at 68 Fahrenheit from the lower to the upper reservoir. So now we have reservoir here, and we have to pump it here. So LU, lower and upper reservoir. Now they say that pipe is steel. Why do they give the pipe is steel for us? Because, you know, like in each pipe it has different characteristics, different specifications. If pipe is made from steel, so the coefficient value or the C value or something value is, like, you know, it depends on that one. If pipe is from plastic, so the friction is not the same as pipe and steel, something like that. So that is very important to know what material is the pipe made from. So now we go on to the solution. We have we need to find the area. So area of the pipe equals to, I guess it is not mentioned in this one. So yeah, another additional. I think I did not copy like total, so sorry. So the additional is additional information. D equals to 8 inches. I think it's like linked with another exercise, so that's the reason that yeah, I'm so sorry. So area equals to 1.4 d squared pi. It's equals to 1.4 multiply by 8 square 8 inches. So I'm gonna write inch square multiplied by 3.142, and then we have the final answer, which is 50.3. Let me check if it's right. 1 over 4 multiplied by 8 square multiplied by pi. Yep, it's 50.265, and I'm just fit square. So now we can find v, which is the velocity of the flow rate, is equals to a. So q equals to av, v equals to q over a, and the q they gave us is 2.5 cfs over 50.265 feet square equals to 2.5 over this one, 265, yeah, 0. Oh, I'm sorry, I made a mistake again. It's inches square, so I need to convert this one to feet. So inches square, so in 1 feet there's 12 inch. So if 1 feet square, this must be 12 square, 144. Yep, 144 inches square. The way I have to 50.265 divided by 144 equals to 0.349 feet square. So you divide 50.265 divided by 144. Yeah, it equals in feet square. So now we have this one, 0.349 feet squared. So 50.265 divided by 0. This one, we get 2.5 divided by 0.3497 equals to 7.1633. Okay, I'll just only give 3 digits, and then we have this one as feet per second. I wonder if you can write this one, FPS, feet per second. Nice. And then we have RE, which is the Reynolds number. Reynolds number equation has RE equals to VD over V, like this. So V is like viscosity. Actually, it is like, it will be provided in a specific, I guess, in a specific table at the end of the exam sheet, or they just give it in the problem, you know. And then we have RE equals to this one. So we have RE, which is the Reynolds number, equals to 7.163 feet per second multiple by d. Inch. But this one, okay, so I'm just gonna do this. H inch equals to 0.666 3 digits feet. 0.66 feet. Okay, so this one equals to 8 over 12, 2 over 3. Okay, and then we have this one in feet over 1.110 feet square per second. So now we have 7.163 multiplied by 0.667 over 1.1 10 to the minus 5. Oh, that's a lot. 4 3 4 3 3 8 2 7. So basically, yeah, the units are cancelled out. So it's equal to 4.3. Okay, 4.35 like this. Yep, 1 2 1 2 5. Okay. So now we have everything done here. So there's no unit here. We can find KS or D equals to 0.0002, and then we have the F, which is the friction. So the friction here equals to 0.016. So these are the given values, that is like the characteristic of the pipe, of the steel pipe. So now let's assume the entrance loss coefficient of 0.5 and the exit loss coefficient as 1. So entrance equals to 0.5, I mean the loss coefficient, and exit equals to 1 loss coefficient. Then we have the HL. So HL here equals to F L over D plus 1.5 V squared over 2G. So this is another new formula again. So for F here is the friction value. I mean the friction coefficient of the steel pipe, and it is over length, which is over feet, which is 0.667 feet here as the diameter, plus 1.5 and then bracket. So now we have the V that we found earlier. It's 7.163 FPS here over 2, and of course it is not the same as G in the unit is a 81 meter square per second, but G in US unit is equals to 32.2 feet per second square. So now we have 32.2 feet per second square and the oval value here. So now let me use the calculator to find out the real answer. 3,000 over 0.667 plus 1.5, and then we multiply the overall thing here was 3 over 32.2. We have 58.5 feet. So now we can let me add another paper. We have to find the rewrite the energy equation from water surface to water surface. So what is water surface to water surface again? It is the H static hat. Okay, with the capital H. So now we have the energy equation. So this energy equation, it is the one that we have learned from before midterm, plus Z1 equals, oh, but this one we have HP equals to P square over this one plus this one, 2G plus Z2 plus HL. So now this is, I'll use another color, 0, 0, 100 feet, and HP is unknown. This one, 0, this one, 0, this one is 150 feet, and this one is 50.5 feet that we found earlier. So now we can find the HP equals to, you know, everything that combined together. Okay, so now we have 108.5 feet. So we can find the P. Again, this is power, not pressure. So P equals to Q HP this way, and it's 2.5 CFS multiplied by 62.4. This is for the US unit, and then we multiply by 108.5 feet. So the final answer here is 2.5 multiplied by 62.4 multiplied by 108.5. We have 6,926 here. Pound, if I'm right, this is pound. And then we convert this one to horsepower, which is equals to wait for a second. So 1 horsepower equals to 547 of feet. Oh, a feet per second. So in order to have this one, we have 16926 divided by 548 point. Did I say 7? Okay. So now it's 30.847 horsepower. So I need to summarize everything again because this is so confusing. Oh, this is only a 2-line problem, but the solution is actually 1.5 pages. Okay, so now additional info. Do I need to okay, additional info of this one. First one, length is 3 feet? Okay, 3,000 feet. Diameter, it's 8 inches. Gravity, 32.2 feet per second square. 1 horsepower equals to 548.7 feet pound per Second, Z1 and Z2. Z1 equals to 100 feet. Z2 equals to 100 feet, like this. I guess that's all for the additional information that we need to use. Oh, viscosity 1.1, 1.1, 10, 5. The unit is in feet square. A second. Okay, so now we have this one. Please try to do it yourself by using all this additional information and combine it with this information here that we have. So now you can finally do this one, and we can move on to another exercise. Okay, so now let's move on to our last problem for today. The problem says that a centrifugal pump provides a flow rate of 500 gallons per minute when operating at 1,750 rounds per meter against a 200 feet head. So this one is flow rate Q, and this one is the angular speed, and this one is head. Okay, so then we have determined the pump's flow rate. So A, determine the pump's flow rate. So we have this equation Q flow rate here, Q1 over Q2. It's similar to what is that called? Transformer, right? Transformer. We have this one over 2. So now we can find the pump's flow rate here. Q2 equals to angular speed 2 over angular speed 1 multiplied by Q1. So in this case, we have, oh, I forgot to show you this one. It's Q. So this is already increased. I mean W, the angular speed. So now we have angular speed 3,500 over angular one. It's where is it? 1,500, 1,750, and multiple by 500 gallons per meter. Per minute. So now we have 35 point. I'm sorry for my prawn head. This one and multiplied by this one equals to 1,000. There must be something wrong with my calculator, or something wrong with my. Okay. It's really 1,000. Nothing is wrong with why is it so large. And then we can find for B, it says determine the developed head if the pump speed is increased. So it's like the developed head is like the head, yeah, the H2 that is like after everything is settled. So determine the developed head. So now we have HA1 over HA2 equals to this one, angular speed 1 over angular speed 2 square. Okay, so now we rearrange this one. We want this one. Oh, we want this one. So put this one here, up here. So now we have HA2 equals to What is happening right now? Okay. Oh well, omega 1 square multiplied by HA1. So now the final answer, this one is previous. It was 3, 5, right? Oh up, 1750. Oh up, okay. And it's multiplied by 200. So now we have 3500 square divided by 1750 square multiplied by 200, which is equals to 800 feet. So this is the final answer for this one. This is for B we have 800 feet, and for A we have 1,000 gallon per meter per minute. Okay, so now we have done so many exercises so far. um we have this formula, the q here, q1 over q2 equals to omega 1 over omega 2 ha1 over ha2 equals to omega 1 square over omega 2 square. And then this is the formula. I will provide the neat handwritten formula again. So now we have this one. We have these the what do we call that? This TDH equals to static head plus friction head plus minor head. Okay, so now let's go through everything again. We have this one. We want to find the TDH and power. So now we have TDH equals to static head plus friction loss plus minor loss. This one again, it's from surface to surface. So if you want that, like, imagine without using the pump here, there's no pump here. So this one will be 2 here plus 35 here and then plus down here. But then you minus this one here. Like it's going down like this and it's going up like this. So we only need 1.5 meter as the surface here. That is compared to it is actually supposed to compare to this one. So you can imagine, like, if this not compared to this one, so this 35 would be something here, like around here. But it is made too easier, so nonetheless, it's still 38.5, okay, and then we find the final TDH here. We can substitute it to find the power that we need to generate the pump, and this is the power that we get. So moving on to the next exercise that we have here, we want to find the modal discharge. So this is another equation that we need to consider. So we have a lot of equations today. I will give you a summary of this equation in the next video. So stay tuned for the next video. Okay, so now we have modal and pump here. We can find this one by rearranging the equation, and then we can get the head rise here by using another. So we have 1, 2, 3, 4, 5 equations so far. 6 equations so far, including efficiency. And then we have the other one here that is actually quite a lot of equations, but they're like the small equations like area, Q equals to AB, Reynolds number, and such as these things. Okay, so now this is the head, is it called a head loss? What was the answer? How horsepower, they were finding the horsepower. So this is how we get this one. So I will attach the blank problem sheet in the description box below, and if you want to try to do it, please feel free to practice on your own, and don't hesitate to ask me if there's any question. I'll be always 24/7 available for you. Okay, that's all for today. Thank you so much. I love you. Bye bye.